All right, welcome to Chapter 7, Exponential Functions. So first we're going to start off by looking at the characteristics of each functions. So they have the form of f of x is equal to a exponent x. Now you've seen this before, but usually it's like the exponent is the base. So like x to the power of 2 or something like that, or 3 to the power of 4, something to that effect. What's different now with exponential functions is we actually have the variable as the exponent. So when we're looking at some vocabulary you've already learned, well, you know the x is the exponent, and then this a is going to be our base. Now all of this together, that forms our power. Now if we look at that base, that's going to be what's really important here. So if a is greater than 1, what will happen to our function? So like examples would be like 2, 3, 4, and so on. I'm going to pick a nice easy number. Let's do 3. So 3 to the power of 1 is 3. 3 to the power of 2 is 9. And 3 to the power of 3 is 27. And that pattern would continue on. So we're seeing the x is changing each time. The exponent is changing. The base is staying the same. Well, we're having a tripling effect here. And that tripling effect is based on what the base is. The base is 3, so it's tripling each time. Now what does that mean? We're growing generally. That's what it means. So whenever our a is bigger than 1, we have some kind of growth happening. Well, what if a is between 0 and 1? So nice easy number is 1/2. So 1/2 to the power of 1, well, that's 1/2. 1/2 to the power of 2, well, that's 1/4. And then 1/2 to the power of 3 is 1/8. Okay, and that continues. Okay, so we're seeing some decrease by half each time. And again, that's based on what our base is. So if this was 1/4, this would be going down a quarter smaller each time. And we call this decay. We're decaying. And our final example is, what if a is exactly 1? Now this one's not that exciting. 1 to the power of 1 is, well, 1. 1 squared is still 1. 1 cubed is 1. Yeah, no change. No surprise. So all of these things happen in real life. So where a is greater than 1, well, this is the one where we're talking about money, interest. So you're putting something into a bank account or into the stocks. You're hoping that they're going to get bigger and it's going to grow. Well, and bacteria also falls into this one as well. So bacteria tends to grow, triple, double, whatever it might be over a certain amount of time. For our second case that we're dealing with, 0 to 1. Well, to me, I think of radioactive materials, and how they get decay over time. So maybe they get half as small over a certain amount of time period. And the last one, a is equal to 1. Again, I'm going to go back to money. This would be like putting money into a checking account that has no interest rate. So even after like 2-3 years, so those time period is the number of years, your money's still the same. There's no change, even though something has passed by. Time has passed by. Our first example is decide whether each of the following functions are exponential. If they are exponential, are they growing or decaying function? So we're looking for where we have some kind of base that is not a variable, but the exponent is actually the variable. So right away, that actually takes out a, because we see the base is the variable, not the exponent. So nope, that's not exponential. Here we have a base of 6 and an exponent that's a variable. Perfect. Yep. That's an exponential function. Now, is it growing or decaying? Well, we have to look at the base. So if the base is greater than 1, it's going to grow. Yep. It's bigger than 1, so growth. C, well, again, we have our base is the variable, not the exponent. So nope, that doesn't work. Now, this one's a little bit tricky for D because we have this negative exponent here. Well, it actually doesn't matter too much as far as determining if this is an exponential function or not, because we still have a base of 4, but we do have an exponent that is a variable. So yes, it is exponential. Now, whether this is growing or decaying, you need to do a little bit of work here. When we have this negative, that means we actually need to reciprocate the base. So this is really 1/4 to the power of x. And now it's more obvious if this is growing or decaying. 1/4 is definitely less than 1, so we have some kind of decay happening here. Our next question. So from previous knowledge, complete and provide a sketch of the graph. So when I say previous knowledge, it's really just meaning I want you to substitute these x values into this function or equation, in this case y equals 2 to the power of x. And that's where this previous knowledge is coming from. I know you haven't really seen that before. So I'm going to go in 2 to the power of negative 3. Well, I'm going to reciprocate the 2, so it's really 1 over 2 cubed. Okay, that's 1 over 8. And then we'll do it one more time. So 2 to the power of negative 2. Again, reciprocate. So it's going to be 1/2 squared equals 1/4. And then we have 2 to the power of negative 1. So again, reciprocate all to the power of negative 1. Or sorry, positive 1. You get 1/2. Now 2 to the power of 0. Anything to the power of 0 is still 1. 2 to the power of 1 is 2. 2 squared is 4. And 2 cubed is 8. So now we need to sketch these values. So we should label this graph a little bit. So we got positive 3 here, negative 3 here. We've got 10 at the top and 3, 4, 5. All right, so we're all labeled. Now to plot these points, so negative 3. Now 1/8 is really, really small. I think it might be easier to start at 1 here. So 0, 1. And then we see at negative 1, we're at 1/2. So kind of half of that. And then it's a quarter, so half of that yet. And an 8 is a half of that yet. Just make sure it's not actually on the axis, because this is never going to hit the axis. You have to think, no matter how many times we keep on having this, it's never going to reach 0. Like, we're going to be a very, very tiny number, but it's never going to be 0, which means we do have an asymptote there of y equals 0. Again, repeating one more time, normally, no matter how many times I take half of something, I will never have 0. Okay, moving on to the positive x values. So we said we get 2, so 1, 2, and then 2, 4, and 3, 8. Now we should connect these. It is continuous, and it does go on forever, so we should put an arrow there. Okay, so looking at our domain then, well, we can actually use any x value. Again, like negative 1,000 might have a really, really tiny y value or height of this graph, but it does still exist. So therefore, we can have negative infinity, and it goes all the way up to positive infinity. This can go on forever. As for our range, a little bit different. We never quite get to 0. We get very, very close to 0. We say it approaches 0. And then on the other hand, as we're going up, it goes on up forever to the largest point possible. Our x-intercept, well, there is none. It's never going to be y equals 0. Again, there's an asymptote there. We do have a y-intercept, though. It occurs at 1. All right, a very similar example, but this time we have a decaying function. So again, from previous knowledge, meaning we're going to use the table to figure out what this is. So I'm looking at 1/2 to the power of negative 1/3. So again, I'll reciprocate my base, so it becomes 2 cubed, which is 8. And then we'll have 1/2 to the power of negative 2. Again, reciprocate, so you get 2 squared, which is 4. And then finally, 1/2 to the power of negative 1. And that's going to be reciprocated to 2, which is just 2. Now, 1/2 to the power of 0. Anything to the power of 0 is just 1. And then we have 1/2 to the power of 1 is 1/2. 1/2 squared is 1/4. And 1/2 cubed is 1/8. So we're going to go and plot those points then. So again, we should label this. This is positive 3, negative 3. This is 5, right? 5 and 10. And plotting these points. Now I'm going to start with this 8. I think it's going to be easier to do the large y values first. So negative 3, 8, negative 2, 4, negative 1, 2. And then we get our y-intercept right here. So we can fill that in. It's still at 1. And then we have 1, 1/2. And it's going to keep on halving each time, again, because our base is 1/2. So then we got 1/4, 1/8. Again, make sure this does not hit the axis. There is an asymptote there. Again, no matter how many times we half this, it's never going to actually get to 0. So that's our asymptote. We have no x-intercepts. Now for our range, again, it can be any x value. I know a positive x value will return a very, very, very small height, but that's okay. It still exists. So we have negative infinity all the way to infinity. For our range, our smallest value we can have is very close to 0, but not exactly 0. That's why there's no square brackets here. All the way to positive infinity on this left side of the graph.